Bismillahirrahmanirrahim. Assalamu alaikum. Now we are going to study our third lecture of chapter number 3, Plasma as Fluids. Our third lecture is about classical treatment of dielectrics. Before this, in our second lecture, we studied the classical treatment of magnetic materials, in which we said plasma is not a magnetic material. Plasma is a diamagnetic material. Okay. Now let's discuss classical treatment of dielectrics. In dielectrics, the positive and negative charges are bound. Mean dielectric does not contain any kind of free electron. As we know, in conductors there are a lot of free electrons, but in insulators or dielectrics there are no any free electron. But when we keep some dielectric inside the electric field, then there is a relatively small displacement between positive and negative bound charges of that dielectric. The phenomena is called polarization, and the material is said to be polarized. And these positive and negative bound charges separated by small displacement are said to make a dipole, dipole. And we know dipole consists of equal positive and negative charges, so dipole does not have any kind of net charge. The magnitude of charge and distance between the charges is called dipole moment, and dipole moment is denoted by P. QD is equal to P. This is dipole moment. The polarization, which is denoted by capital P, per unit volume is the sum over all the individual moments of the electric dipoles. This gives rise to a bound charge density. For dielectric, charges are still bound. In the presence of electric field, although there is a relatively small displacement between positive and negative charges, but still the charges are bound charges. And the bound charge density is given by sigma B is equal to del dot P. Del dot P. P here is polarization. The dot product of del and polarization is called bound charge density. This is our equation number 1. Again, for vacuum. For vacuum, Maxwell's first equation is given by epsilon naught del dot E is equal to sigma. This sigma will be written as the sum of bound charge density and free charge density in very much similar manner as we said in classical treatment of magnetic materials, in which we modified in which we included bound and free current densities in the equation number 4 of Maxwell's equations for vacuum. But here we are going to use first equation for vacuum. Epsilon naught del dot E is equal to sigma, and this sigma, here we must add both the bound charge densities and free charge densities here in this sigma. What we get? So equation number 1 becomes epsilon naught del dot E is equal to sigma F plus sigma B. Sigma F plus sigma B. We replace sigma by sigma F plus sigma B. Sigma F is the volume charge density for the free charges, and sigma B is the volume charge density for the bound charges, and this is our equation number 3. We wish to write this equation number 2, in simple form. We wish to write this equation in the simple form, and simple form is del dot D is equal to sigma F. This is Gauss's law for dielectric. You have already studied Gauss's law for dielectrics. Del dot D, here D is a displacement vector. Del dot D is equal to sigma F. This is our equation number 3. We include, by including sigma B in the definition of D. Now we shall include the bound density in the definition of D, as we did. I remind you what we have done in our second lecture, classical treatment of magnetic materials. We included bound charge density in the definition of H, and then we cancelled sigma JB from both sides. In similar manner, following the same lines, we are going to include sigma B. This is volume charge density, sigma B, in the definition of D, displacement vector. This can be done by letting displacement vector D is equal to epsilon naught E plus P. This formula we already know. Displacement vector is equal to sigma epsilon naught E plus P. E is the electric field and P is the polarization. So D is equal to epsilon naught E plus P, or we can write epsilon E. Epsilon E, this is our equation number 4. Equation number 4. From this relation, we can see P is, polarization is linearly proportional to E. Mean greater the electric field applied, greater would be the polarization. Greater the electric field, greater would be the polarization inside the dielectric. So P and E are directly proportional to each other, or P is equal to epsilon naught chi E into capital E. This is our equation number 5. Remember this one. P is equal to epsilon naught chi E to capital E. This is our equation number 5. Putting value of P in equation number 4, displacement vector D is equal to epsilon naught E plus, here P has been replaced by its value epsilon naught chi E. Epsilon naught chi E, this is the value of P. we put in equation number 4, and here we can see epsilon naught is the common from both these terms, so we get epsilon naught into 1 plus chi into e. This e is also common, so d is equal to epsilon naught into 1 plus chi into e, where epsilon is equal to 1 plus chi into epsilon naught. This is epsilon, dielectric constant. There is no priori reason why a relation like equation number 5, you know, was p is equal to epsilon naught chi into e. This was our equation number 5. So what we concluded, there is no priori reason why a relation like equation number 2 cannot be valid in a plasma. So we may proceed to try to get an expression. For epsilon in a plasma. In our next lecture, we shall establish a relationship for epsilon, inshallah. It's okay. Allah Hafiz.